Here we have also considered another problem. This is a very simple problem, and from the basic knowledge of Euclidean space, I have taken the classes of orthogonal and orthonormal basis, or orthogonal or orthonormal collection of sets as a preliminary in the preliminary sessions, and from that very section I have considered a problem here. Here you have given two sets. First set of vector this is, second set of vector this is, and you have asked to show this first one is an orthogonal collection of vectors and the second one is an orthonormal collection of vectors. And we all know how to check a collection or set of vectors is orthogonal. The definition, try to remember the definition of orthogonal set of vectors. The orthogonal set of vectors, from a orthogonal set of vectors, if you consider any two distinct members, that means any two distinct vectors, the inner product of those very vectors would be equal to 0, and there nothing has been mentioned about the same vector. That means if you consider the inner product having same component, the component vector being from the very collection which has been given, nothing has been mentioned in case of orthogonal collection. But in case of orthonormal collection, the same component, for the same component inner product, the inner product value would be equal to 1. The first one you have to show that this is an orthogonal collection. So you have to show the inner product between two distinct members from this collection is 0. And about the inner product, there has nothing been stated. That means you have to consider the standard inner product. And each and every vector being having three components, each and every component being a real number, this is from R3 Euclidean space with the standard inner product. We are renaming this first vector, or taking this first vector 3, 0, 4 as alpha 1 vector, the second vector minus 4, 0, 3 as this alpha 2 vector, and the third vector 0, 9, 0 as this alpha 3 vector. And now we are calculating, here we have calculated first the inner product of alpha 1 and alpha 2 vectors, that means alpha 1 comma alpha 2. This is equal to the first component of this alpha 1 vector being 3 and first component of this alpha 2 vector being minus 4. The first member is 3 into minus 4 plus the second component of alpha 1 0 into the second component of this alpha 2 vector 0, that is 0 into 0, plus the third component of alpha 1 vector being 4 and the third component of this alpha 2 vector being 3, this is a plus 4 into 3. And after simplification we have this value equal to 0. Similarly, we have calculated this alpha 1 comma alpha 3, the inner product alpha 1 comma alpha 3, and its value is equal to 0. And also we have calculated alpha 2 comma alpha 3, this inner product, and the value of this inner product is also 0. So the inner products, distinct inner products having two components distinct from this collection, first set of vectors, we have obtained for the each and every inner product value is equal to 0. That means we can say the collection of vectors alpha 1 comma alpha 2 comma alpha 3 is an orthogonal collection of vectors. That means the collection of vectors 3, 0, 4, minus 4, 0, 3, 0, 9, 0 is an orthogonal set of vectors. And the second set of vectors 1 by 5, 3, 0, 4, 1 by 5, minus 4, 0, 3, 0, 1, 0. This set of vectors is an orthonormal vectors. To check this orthonormal, similarly, we have to calculate these three portions. For distinct members, that means the inner product whose two components are being distinct, would the value of that very inner product would be equal to 0. We have to show this as we have shown in this orthogonal case. And we have to show in this orthonormal collection, to show this is a orthonormal collection, the norm of this each member is equal to 1. That means as we have done the process to show this collection of vectors as orthogonal, we have to do the same process, and an extra thing we have to show, that is the norm of this each vector is equal to 1. So let us now first calculate the norm of this each vector. Okay. Suppose we are taking the first vector as a beta 1, that means beta 1 equal to 1 by 5, 3, 0, 4. The first vector 1 by 5, 3, 0, 4, we are taking this vector as the beta 1 vector. The beta 1 vector equal to 1 by 5, 3, 0, 4. The second vector 1 by 5, minus 4, 0, 3, we are taking this vector as the beta 2 vector. Beta 2 vector equal to 1 by 5, minus 4, 0, 3. And this third component, third member 0, 1, 0, we are taking this vector as the beta 3 vector. And now we are calculating the norm of each vector. The norm of beta 1 vector, we all know how to calculate the norm. This is equal to root over the addition of all the squared components of these beta 1 vector. What I have said, norm of beta 1, this is equal to root the addition of each squared component. That means we are taking the square of this each component and adding them. So norm of beta 1, this is equal to 3 by 5 whole square plus 0 square plus 4 by 5 whole square. The calculated value is equal to 1. Similarly, we have calculated norm of beta 2 vector, this is equal to 1, and similarly the norm of beta 3 vector is also 1.